In this measurement lesson, we're going to go through quite a few topics. We're going to go through how to write from decimal to scientific notation. We're going to go through a foolproof method of converting between units and an extremely easy way to remember the 12 SI prefixes, introduction to significant figures, how to figure out the number of Sig Figs, how to present the answer in the correct Sig Fig or decimal place when doing addition, subtraction, multiplication, or division, density, the formula, and some real-life examples, and finally, temperature, converting between Celsius, Kelvin, and Fahrenheit. Without further ado, let's get started. In this video, we're gonna write numbers in scientific notation. Before we get started, let's figure out what is scientific notation. Imagine you have numbers like this. It's kind of hard trying to say or write them out, right? That's where scientific notation comes in. Here I have 2.5 times 10 to the power of 11. There's a format to writing it this way. First off, there's this decimal point that we need to pay attention to. Now, in front of that decimal, there should be only one digit. That one digit should go from 1 to 9. 0 or 10 is not acceptable. And then after that, you figure out what's the exponent value. It should be either a positive or negative integer, which is numbers like -2 or +3 or so on. Let's convert this huge number into scientific notation. We need to place in the decimal point, which is located all the way at the end of the number. And then we need to move the decimal all the way to the left until there's only one digit right before it. So right now we have 12 digits in front of the decimal, so we need to keep moving it all the way until 1. So in total, we move 11 steps. So we write 1.4 times 10 to the power of 11. It's 11 because we move 11 steps, and it's positive because we move to the left. The exponent is positive when the number is greater than 1. In this case, 140 followed by 9 more zeros is definitely greater than 1. Now let's try and convert this very small number into scientific notation. In the previous example, for a large number, we moved the decimal to the left because there were a lot of numbers in front of the decimal point, right? In this example, the decimal place is here. There are 9 zeros before the number 257, so we'll need to move the decimal to the right all the way until there's one digit before the decimal point, meaning we'll need to move it until right after the number 2. Since we move it to the right 10 times, the exponent will be -10. The scientific notation of this number is 2.57 times 10 to the power of -10. Now it's negative exponent because it's a very small number that is less than 1. To recap, for a large number, we move the decimal to the left, we count the number of places moved, and write that number in positive exponent. For a small number, we move the decimal to the right, count the number of places moved, and write that number in negative exponent. In this video, we're going to go through how to do metric conversion involving one prefix, like picosecond going to second, meter going to megameter, centimeter cube going to meter cube, just to name a few. I'm going to share with you a foolproof method and tips to make sure you'll be able to do the conversion successfully. Let's get to know some of the common SI prefixes. I've included 12 of them, from tera all the way to pico. Depending on your school, you might need to memorize them. Tera, giga, mega, all the way to pico, those are the names of the prefixes. And the numbers are the value for each of the prefixes. For example, 10 to the power of 12, that is the value for tera. 10 to the power of 9 for giga, and so on and so forth. I've also included in base, which has a value of 10 to the power of 0, which is the same as 1. Sometimes when you see prefixes being used, they are abbreviated like this, like capital T to represent tera, small letter d to represent deci. So how do we use prefix and base? Let's take kilometer for example. That's a unit for distance. So meter in this case is the base unit. K, which stands for kilo, is the prefix. To make life easy, I came up with a mnemonic to help you remember all the 12 prefixes. That should help you remember the name of the prefixes in the correct order. The great man King Henry's daughter, Bev, drinks cold milk until 9 p.m. I've worked off from the abbreviation for each of the prefixes starting from tera all the way to pico. As for the numbers on the exponent, we will start out with 0 for base and then 1, 2, 3, 6, 9, 12 on each side. The difference between the left side and the right side, on the deci, centi, milli all the way to pico, there's negative sign in front. So if you remember, the great man King Henry's daughter Bev drinks cold milk until 9 p.m. and then you go from 0, 1, 2, 3, 6, 9, 12. Do that on both sides and then make sure you put in the negative sign for the right hand side, which is deci all the way to pico, and you'll successfully memorize all 12 SI prefixes. Hope this helps. Now that we know our prefixes, let's proceed to the metric conversion. I went through a foolproof method of unit conversion in a video I've posted. The link is on the top right corner and in the description box below. Do check it out if you haven't seen it. So we're going to proceed using this method, and so let's start with our first example. Question is asking us to convert 936 picosecond to second. If you recall from our SI prefixes, the value for pico, which is P, it's 10 to the power of negative 12. So what this means is 1 picosecond is 10 to the negative 12 s. Second is the base unit in this case. Pico is the prefix. So we're trying to convert picosecond to second. Now that we know the conversion factor, we can easily convert. Start with what is given, which is 936 picosecond. Multiply, draw a line across, place the unit that you want to get rid of at the bottom, which is picosecond, and then place the unit that you want, which is second, on the top. Picosecond will cancel each other off, and then after that we place in the values. From our conversion factor, we have 1 in front of picosecond, 10 to the negative 12 in front of s. So we do the math. 936 times 10 to the power of negative 12 divided by 1. That will give us 9.36 times 10 to the power of negative 10 seconds. Let's try on another example. Convert 25 meter to megameter. So the question is asking us to convert from meter to megameter. Again, from the prefix table, mega, the value is 10 to the power of 6. So what this means is 1 megameter is 10 to the power of 6 meter. Meter is the base unit in this case. So start with what we have, which is 25 meter, multiply, draw a line across, put meter at the bottom, and megameter on the top, because we want to cancel off the meter, giving us megameter. And then we place in the values in front of the units. 1 in front of megameter, 10 to the power of 6 in front of meter. So that gives us 25 times 1 divided by 10 to the power of 6. If you punch it in your calculator, or if you can do mental math, that will give us 2.5 times 10 to the power of negative 5 megameter. Moving on to our third and final example, it's slightly more difficult than the last two that we've tried. So this question is asking us to convert 25 meter cube to megameter cube. The previous example, we were asked to convert from 25 meter to megameter. Do you see the difference? Do you think we're going to get the same answer like the last one, which is 2.5 times 10 to the power of negative 5? Except for the unit now will be megameter cube? Well, stay tuned and we're going to go through the calculation. Let's start with the prefix mega. Mega is 10 to the 6. So 1 megameter is 10 to the 6 meter. Then we start with what's given, which is 25 meter cube. And then we multiply, draw a line across, and then we place meter at the bottom and megameter at the top, because we want to try and cancel off the meter. So we place the meter at the bottom and we place in the values for the conversion factors. So far it's the same steps as the previous example, but now notice that the unit for 25 is meter cube. So that means we need to cube everything as well, so that meter cube will cancel off meter cube, like this. So let's simplify. Now we have 25 times 1 divided by 10 to the power of 18, because we cube the exponent 10 to the 6 cube, So 6 multiplied by 3 gives us 18. And then the meter cube can now cancel off each other. And we do the math, we get 2.5 times 10 to the power of negative 17 megameter cube. That is definitely not the same as the answer that we got from the previous example. This kind of conversion that involves cube or square, a lot of people make mistakes when trying to solve this because they miss out that cube part. So when you perform calculations that has cube or square, please make sure after you've placed in the conversion factor, make sure you cube it or you square it, whichever that's appropriate. In this video, we're going to look at the basics of significant figures. Knowing how to determine the number of significant figure is important when performing calculations related to science and engineering. There are 5 guidelines that will help determine the number of significant figures, or we call it Sig Fig for short. The first one is, any numbers that are not 0 are significant. For example, 987. There are 3 non-zero numbers. That means 987 has 3 Sig Fig. The second rule, leading zeros are not significant. Leading zeros mean the zeros that lead up to a non-zero number. So in our example, it's those 3 pink zeros that lead up to 987. So that means those 3 pink zeros are not significant. Therefore, 0.00987 has 3 Sig Fig. The third rule, trailing zeros to the right of decimal are significant. In 98.700, the 2 zeros that appear after the decimal point, they are the trailing zeros and they are significant. That means we have a total of 5 Sig Fig. The fourth rule, trailing zeros in whole number without decimal are not significant. 9870 without decimal point, that 0 is not significant. Therefore, 9870 has only 3 Sig Fig. Last but not least, the fifth rule, trailing zeros in whole number with decimal point, they are significant. Meaning, in 9870 point, that 0 that appears in the whole number that has that decimal point, that 0 is significant, which means 9870 point has 4 Sig Fig. Let's try out a few questions. Feel free to pause the video and try out on your own first. We'll go through them together when you're ready. Ready? The first question, 127.01 has 5 Sig Fig. That 0 that is sandwiched between non-zeros 7 and 1, that 0 is significant. So which means 127.01 has 5 significant figures. The second question, 0.0005210. The 4 zeros that lead up to 5210, those 4 zeros are not significant because those are the leading zeros. That 1 0 that appears after the decimal point, that is significant. Therefore, 0.0005210 has 4 Sig Fig. The third question, 376,000,000. This number has 6 trailing zeros. Those 6 trailing zeros is in this whole number that doesn't have any decimal point. That means it has 3 Sig Fig. We're following rule number 4 in this case. Fourth question, 48000 point. 48000 point has 3 trailing zeros. Since this whole number has a decimal point, these 3 leading zeros are significant, following rule number 5. Therefore, 48000 point has a total of 5 Sig Fig. Last but not least, 1.750 times 10 to the power of negative 4 is written in a scientific notation. For any number that's written in scientific notation, we only look at the number before the exponent. In this case, it will be 1.750, and we apply the same 5 rules. So looking at 1.750, there's a 0, there's a trailing 0, which appears after a decimal. Following rule number 3, it is considered as significant. Therefore, 1.750 times 10 to the negative 4 has 4 Sig Fig. Keep these 5 rules in mind when trying to figure out the Sig Fig, and you'll be all set. In this video, We'll go through the rounding rules for significant figures when performing calculations like addition, subtraction, multiplication, and division. The rule for addition and subtraction is to round off following the lowest decimal place. Decimal place refers to the number of digits after the decimal point. Let's look at this example for addition. We have 987 plus 98.7. 987 has 0 decimal point because there is no digit that comes after the decimal point. 98.7 has 1 decimal point because there is 1 digit after the decimal point. Since the rule is to round off following the lowest decimal place, our answer should be presented in 0 decimal place. When we add up these two numbers, we get 1085.7. We need to round it off so that we get 0 decimal place, so we look at the digit to the right of 5, which is 7. When rounding, if the number is 5 or greater, we need to round up. In our case, we have 7. That means we need to round up, and that will give us 1086. We add 1 to 1085 and we remove everything that comes after the decimal point, so we get our answer in 0 decimal place. Next, we look at the subtraction example. The same rule applies. 987 has 0 decimal place and 98.70 has 2 decimal place because there are 2 digits that come after the decimal point. Following the rule, our answer will be presented in 0 decimal place. We look at the digit after the decimal point, which is 3. And since 3 is less than 5, we don't need to round up. So our final answer is going to be 888. For multiplication and division, the rule is to go with the lowest significant figure, or Sig Fig for short. So instead of looking at the lowest decimal place like when we did the subtraction and addition, for multiplication and division, we look at the lowest significant figure. Let's look at the first example, 987 times 0.98. Since we need to round off to the lowest Sig Fig, we need to figure out what's the Sig Fig for each of these numbers. 987 has 3 Sig Fig, 0.98 has 2 Sig Fig. If you need a refresher on figuring out Sig Figs, I'll link the intro video in the description box below. The rule for multiplication is to round off following the lowest Sig Fig. In our case, between 2 Sig Fig and 3 Sig Fig, 2 is the lowest, so therefore, our answer is going to be presented in 2 Sig Fig. We multiply 987 with 0.98 and we get 967.26. The first Sig Fig is 9 and the second Sig Fig is 6. That means we need to look at the digit after the second significant figure and decide whether to round up or not. Since that digit is 7, it's 5 and above, so we need to round up. Rounding up is going to give us 970. We add 1 to 6, so therefore we get 970. Looking at the division example, we have 987 divided by 0.9. We follow the same rule, which is to round off to the lowest Sig Fig. So the first number, 987, has 3 Sig Fig, and the second number only has 1 Sig Fig. So therefore, our answer is going to be in 1 Sig Fig. So when we take these two numbers and we divide, we get 1096.67. Rounding it off to 1 Sig Fig, that means we need to look at the second digit, which is 0. 0 is less than 5, so that means we don't need to round up. So presenting the answer in the correct Sig Fig form is going to be 1000. So far, we've gone through examples involving only single operation, meaning it's just purely multiplication, division, subtraction, or addition. If you encounter a question that has mixed operations, just follow the order of operations, keep track of the decimal place or Sig Fig for each step, and then round off at the very end. Don't round off for each step. Keep all the digits and only round off at the very end. Let's try out a few questions. Feel free to pause the video while solving it on your own first. We'll go through them together when you're ready. Okay, ready? Let's start with the first question. It's an addition question. For addition, the round-off rule is to follow the lowest decimal place. So that means we need to figure out the decimal place for each of the number. 123.4 has 1 decimal place. 0.789 has 3 decimal place because there are 3 digits after the decimal point. So that means our final answer will have 1 decimal place. When we add the two numbers together, we get 124.189. One decimal place means one digit after the decimal point, which means in our case that's the 1. So we look at the digit to its right, which is 8, and then we decide whether we need to round up or not. Since 8 is 5 and above, we need to round up, and that gives us 124.2 presented in one decimal place. The second question is a multiplication question. So for multiplication, we round off following the lowest sig fig. In this case, we need to figure out the sig fig for each number. 23.8 has 3 sig fig, 0.1 has 1 sig fig. That means our final answer is going to be in 1 sig fig. So we multiply these two numbers and we get 2.38. To round off to 1 sig fig, we look at the digit to the right of 2. Since it's a 3, which is less than 5, we don't need to round up. The final answer is 2 in 1 sig fig. The third question involves multiple operations. We have a parenthesis. Inside the parenthesis, we have a subtraction. Outside of the parenthesis, we have division and addition. In situations like this, we need to follow the order of operations. PEMDAS is a good guide to use. I'll link the video if you're interested. So we need to solve the operation that's inside the parentheses first. Since it's a subtraction, we're going to have to look at the decimal place. 61 has 0 decimal place, 0.5 has 1 decimal place. That means the result from this subtraction is going to have 0 decimal place. At this point, we don't want to round off anything yet. We just keep all the digits and continue on with the rest of the calculations. The results from the subtraction should be in 0 decimal place, which means 60.5 should actually be 61. But at this point, we don't want to round anything off yet. But keeping that in mind, 61 has 2 sig fig, and then 32.8 has 3 sig fig. So if we were to divide these two numbers, we're going to follow the lowest sig fig, which is going to be 2. So after we divide these two numbers, our answer should be presented in 2 sig fig, which means 1.8. The rest of the digit, we're not going to round off yet. We're just going to keep it and continue on with the rest of the calculation. The last operation we have to do is addition. So we have 1.8445 plus 19. Since it's addition, the round off rule is to follow the lowest decimal place. So 1.8 has 1 decimal place, 19 has 0 decimal place. So which means our final answer needs to be reported in 0 decimal place. So adding these two numbers up is going to give us 20.8445. So 0 decimal place means we don't need anything that comes after the decimal point. So we look at it, it's 8. So since 8 is 5 and above, we need to round up. So that's going to give us 21 as our final answer in 0 decimal place. That's the answer that we have for all the 3 questions. How did you do? Did you get them all right? To recap, when adding or subtracting, we round off following the lowest decimal place. When multiplying or dividing, we round off following the lowest significant figure. In the event that we have multiple operations, just follow the order of operation, like PEMDAS. Keep tabs on the decimal place or the significant figure, depending on the operation that you're doing, and only round off at the very end. Don't round off at each step of the calculation. When trying to round off, we only need to round up if the digit is 5 or larger.
In this video, we'll go through how to calculate density using 2 examples. In one of the examples, we will also touch on measuring volume through water displacement. So stick around until the end if you're interested in that. First off, here's the formula for density. It's pretty straightforward actually. It's mass divided by volume. Normally, density of solid is expressed in grams per cm cube, while for liquid it's grams per ml. These two units are actually the same numerically because 1 cm cube is actually equals to 1 ml. It's just that when you measure the volume of solid, it's calculated in units of length cube, meaning like cm cube, meter cube, whereas for liquid, it's usually measured in milliliter, so that's why there's a difference in the unit for the density of solid and liquid. For density of gas, it's usually expressed in grams per liter. That's because gas is less dense than liquid, so if the density of gas is also reported in grams per ml, the value would be very small, which is not very convenient to write. So that's why it's normally reported in grams over liter. Okay, so now that we know the formula, let's talk about density. What are some of the examples of density that are being applied in our daily lives? Well, the first that I can think of is iceberg. We see frozen fresh water floating in seawater. Now, the frozen fresh water has lower density than seawater, and that's why it floats. Another one that will be familiar would be ice soda. We have ice floating in our soda. The reason the ice floats is because the ice has lower density than soda water. The third one, which may not seem related to density, is vaccine or medicine. So what does density have to do with needles and vaccine? Think about this. Whenever you get a jab for something, right? A vaccine for hepatitis or a vaccine for tetanus, I don't know, just something. Have you ever seen the doctor or the nurse weigh out the mass of the vaccine? No, right? It's always measured using a syringe, correct? Well, that's because it's easier to measure the volume of a liquid than to measure the mass of a liquid. So that's why the vaccine is always measured using the syringe. So how do we know how much volume to draw out? Well, it can be easily calculated when the density of the vaccine is known. In fact, let's go ahead and do an example. Let's assume that we need to administer 1.2 grams of vaccine X. Knowing that vaccine X has a density of 0.785 grams per ml at 20 degrees Celsius, we can calculate the volume that we can easily measure out using the syringe. So let's start with the formula for density, which is mass over volume. But since we want to calculate volume, let's rewrite the formula a little bit, rearrange it. So I bring volume up, so then it becomes volume equals mass over density. Now let's plug in the values that we have. We have 1.2 grams for the mass and 0.785 grams per ml for the density. And dividing these two numbers will give us 1.5. And if we cross out the unit, it will leave us with ml. So the volume is 1.5 ml. So we can easily draw out the volume of 1.5 ml using syringe. Much easier than if we were to measure out 1.2 grams. Make sense? This is a really direct, simple problem related to density. Now let's look at another density-related problem that's a little bit more difficult. So we have a task here, which is to figure out whether the crown is made out of pure gold or not. And we're given two masses. The mass of the crown in the air, that's 4258 grams, and the mass of the crown in water, that's 3926 grams. And then we are also given two densities for our reference. One is for gold, and the other one is density of water. And we're given the look of the crown. So it looks like a gold crown, and we're trying to figure out whether that's pure gold or not. So to figure out whether it's pure gold or not, we basically have to figure out the density of the crown, and then we compare it with the density of gold. So if we figure out that the density of crown is somewhere near really close to 19.31, we can conclude that the crown is made out of pure gold, right? So you might be wondering, why are there two masses given for the crown? What's the purpose of it? Well, take a look at the crown. Will you be able to measure the crown's volume? I mean, it's not a perfectly shaped cone or a rectangle. So we can't apply a formula to come up with the volume. So what we're going to have to do is we're going to displace water and measure its volume that way. So we're going to use Archimedes' principle to figure out the volume of our crown. So we start off by measuring the mass of the crown in the air, and that's 4258 grams. So what we do is then we fill up a tank all the way up to the spout with water, and then we submerge the crown. So once we submerge the crown, some water will be displaced out. That means we can use the mass of the displaced water to calculate the volume of the crown. This is sometimes referred to as volume by water displacement. It's a popular method to figure out the density of odd-shaped object. So let's see how we're going to figure out the volume of our crown using this way. We start off by subtracting the two masses that were given. That will help us figure out the mass of the water displaced. So the mass of the crown in the air is 4258 minus the mass of the crown in water, which is 3926. Subtracting these two numbers will give us 332 grams. So that is the mass of the water that is displaced out. Now, since we know the mass of the water and the question gave us the density of water, we can easily figure out the volume of the water that's displaced. So volume is equals to mass over density. We just simply rewrite the formula of density. So plug in these numbers will give us 332 ml. Since the water that is displaced out is due to the submerged crown, we can conclude by saying that the volume of the crown is also the same as the volume of the water that is displaced out, which is 332 cm cube. Notice I just changed the unit ml to cm cube because I'm now talking about the crown. Crown is a solid object, so I'm using the appropriate unit for solid. So now that we have found the volume of our crown and we know the mass of our crown, the one that's in the air, we can apply the density formula and we can figure out what's the density of the crown. So we take the mass, which is 4258 grams, divide by 332 cm cube, and that will give us 12.8 grams per cm cube. Now compare the density of the crown that we just calculated with the density of gold. Gold is 19.31. What do you think? Is the crown made out of pure gold? Sadly, no. So looks like the crown is not made out of pure gold. So these are two examples to show you how density can be used in real-life application. Just to recap, density is mass divided by volume.
In this video, we're going to look at how to convert between temperature units. We'll be converting using Celsius, Fahrenheit, and Kelvin. Three of the most common units used in measuring temperature are degree Celsius, degree Fahrenheit, and Kelvin. Depending on which part of the world you're in, temperature in your daily lives is measured in either degree Celsius or degree Fahrenheit. Kelvin, on the other hand, is mostly used when expressing temperature in science, as it's the SI unit. The conversion between these three units are rather straightforward. We'll start with converting degree Celsius to Kelvin. All we have to do is add 273.15 to the temperature in Celsius. That will give us the temperature in Kelvin. And if let's say we're given the temperature in Kelvin and we're asked to convert it to Celsius, all we have to do is rearrange the formula, and now all we have to do is subtract 273.15 from the temperature that is given in Kelvin, and that will give us the temperature in Celsius. Converting from Celsius to Fahrenheit requires multiplication of the temperature in Celsius with 1.8, and then we add in 32. If we need to do the reverse conversion, meaning from Fahrenheit convert to Celsius, all we have to do is rearrange the formula a little bit, and we get subtract 32 from the temperature in Fahrenheit, and then divide the whole thing with 1.8. Basically, all we have to do is remember the conversion from Celsius to Kelvin and Celsius to Fahrenheit, and then we can interconvert back and forth between the three units. Let's try out a few conversions. Here we have 3 questions. Feel free to pause the video and solve it on your own first. It won't take too long. We'll check your work together once you're ready. Ready? Here we go. The first question is asking us to convert the temperature from Celsius to Fahrenheit. Referring to our formula, we need to multiply the temperature that's given in Celsius with 1.8, and then we add 32. We plug in 35 to the formula and we get 95 degrees Fahrenheit. The second question is asking us to convert from Kelvin to Celsius. This is the formula that we need. We just have to subtract 273.15 from 298.50, and that gives us 25.35 degrees Celsius. The third and the final question is asking us to convert from 29 degrees Fahrenheit to Kelvin. We don't have a direct formula that will do this conversion. However, we can get the job done by first converting Fahrenheit to Celsius, and then from Celsius we convert it to Kelvin. So we plug in 29 degrees Fahrenheit in the first formula, and we get negative 1.67 degrees Celsius. Using that negative 1.67 degrees Celsius, we plug in the second formula, and that will give us 271.5 Kelvin as the answer. How did you do? Did you get them all right? If not, what went wrong? To recap, here are the formula to convert between the different units of temperature. Remember that you don't need to memorize all the 4 formulas. Just remember 2 of them, it's more than enough. One from the Celsius Kelvin conversion, and another one from the Celsius Fahrenheit conversion. And you'll be all set to interconvert between these 3 units. Thanks for watching all the way till the end. Do subscribe, like, and share this video if you find it helpful. It'll help the channel grow, and I'll really appreciate it.